So every week I get one email and about 24 YouTube comments from people challenging me, saying that because of the radiation in the Van Allen belts, we obviously didn't go to the moon, because there's no way we could possibly go through them without dying, and because this one NASA engineer in a video like 4 years ago apparently admitted that we don't have the technology to go through the Van Allen belts. And I've already done a video on this, but apparently it's time for a revisit. So let's do this, today on Vintage Space. Okay, so the Earth has this amazing thing called a magnetic field. Think of it like a lovely protective envelope protecting our planet from all the deadly radiation from deep space and from the sun. Without it, our planet's atmosphere would be stripped away, much like Mars's, and we'd probably all have cancer, but we wouldn't have an environment to actually be living on the planet anymore, so the magnetic field is a very good thing. Unfortunately, that magnetic field also traps the same radiation that it shields us from. James Van Allen first found evidence of radiation at high altitudes near the poles with Raccoon launches in the early 1950s. Follow-up observations from instruments on board the Explorer 1 satellite in February of 1958 allowed him to discover the high radiation environment, the belts that bear his name, which are two distinct donuts that originate at the Earth's poles and loop around the planet. And more recent data from the Van Allen probes found that a third belt can sometimes appear. Immediately after their discovery, it became clear that the Van Allen belts would be problematic for manned missions leaving the planet. Of course, there's a very simple solution to this: just don't go through them and don't leave the planet. If you keep your mission below 345 miles, which is where the inner Van Allen belt starts, you're still within the Earth's protective magnetic field, and you won't have to deal with the issues of radiation in deep space. But then in 1961, President Kennedy said that America was going to land a man on the moon, and that meant flying through the Van Allen belts. You can't go to the moon without going through the belts. So not only were the astronauts going to be exposed to the radiation of deep space, they were also going to have to be exposed to that high radiation environment passing through the Van Allen belts. Van Allen himself came up with a very interesting solution to this problem, and that was to nuke them. Yep, he wanted to nuke the Van Allen belts. He proposed this idea in July of 1962 in an address to the American Rocket Society on the issue of radiation and Apollo. He suggested that detonating a nuclear bomb in the inner belt, which was the more dangerous region for humans in terms of radiation, could actually clear out the radiation. The added material could give the particles extra energy, enough that it would be able to escape the Earth's magnetic field. NASA didn't try this, which is probably a very good thing, because also in July of 1962, the Atomic Energy Commission accidentally almost nuked the Van Allen belts. The fishbowl events under Operation Dominic were designed to see what would happen if a nuclear bomb was detonated in the upper atmosphere. Remember, we're in the Cold War here, and both sides had nuclear bombs, and we're trying to gain as much understanding of what was going to happen in the event of nuclear war as possible. The Starfish Prime event was launched on July 10th of 1962 and saw a 1.4 megaton bomb detonated at an altitude of 250 miles, so a little bit higher than the ISS orbits today and a little bit lower than the inner Van Allen belt. And it added a lot more radiation to that inner belt. Luckily, the added radiation had dissipated by the end of the decade, so Apollo didn't have to deal with the added radiation environment, because that would have been a real problem for crews. NASA knew that it would be launching crews through the Van Allen belts. That was completely unavoidable. So in addition to adding radiation shielding to the spacecraft, especially the main command module where the crews would be spending most of their time, the agency came up with mission rules. Basically, this was a series of rules dictating what action should be taken if there was a significant solar event during a mission. That's a solar flare that would add significant radiation to the Van Allen belts or just to the space between the Earth and the Moon. The only time a solar event could actually stop a mission was if it hadn't launched yet. There was a mission rule allowing for a hold of the launch vehicle on the pad if a significantly large solar flare was detected. Otherwise, the mission rules dictated that you continue on with the flight, but consider the individual case. So if there was a solar flare while the crew was in Earth orbit, there was a mission rule saying maybe hold off on the translunar injection burn for one more orbit, giving the radiation time to dissipate. If there was a solar flare while the crew was around the moon, maybe consider bringing them back earlier. But in every case, the mission rule said just continue the mission. So with radiation shielding in the spacecraft, mission rules in place for dealing with solar flares, and a launch schedule that took advantage of decreased solar activity, NASA sent astronauts through the Van Allen belts to the moon. And in 1973, it released an experience report talking about the radiation and Apollo. The report, entitled Apollo Experience Report Protection Against Radiation, looks specifically at data from Apollos 7 through 15 and determines that there was absolutely no intensive radiation hitting the crew enough that they would have any adverse effects. And NASA can say that with certainty because the astronauts all wore, and the spacecraft was fitted with, specially designed dosimeters. Each astronaut wore a personal radiation dosimeter in his flight coverall, and also 3 passive dosimeters placed in garments worn throughout the mission. But first, we actually have to look at how radiation is measured, and here's where it gets fun. And by fun, I mean messy. Radiation is measured in a number of different ways. X-rays and gamma rays are less damaging to tissue than neutrons or alpha particles, and there's also a distinction between when radiation just radiates on its own and when it hits human or biological tissue. There's also a difference between the dose emitted and the dose absorbed. If you're right next to an X-ray at, say, 1 rad, you'll absorb more radiation than if you're 10 miles away. And the cherry on the cake is that there is no clear conversion between all the different ways of measuring radiation. Here's the chart showing some ways radiation is measured. There are grays, rads, rems, sieverts, becquerels, counts per second, and curies. And they don't totally relate to one another. Not exactly the cleanest conversion table you could hope for, eh? Add to that sieverts are the measurement that is usually used when discussing radiation's effect on human tissue or biological tissue, but of course, NASA published its results using rads. So let's look at another conversion table to kind of put these two things into perspective. A more modern article about radiation from MIT, aka published this century, states that the radiation dose of 500 millisieverts is when you start to get symptoms of radiation poisoning. So let's look at where millisieverts work with rads. Now remember, there's different conversions for different types of radiation. When we're talking about X-rays and gamma rays, 1 rad is equal to 10 millisieverts. For neutrons, 1 rad is anywhere between 50 and 200 millisieverts. For alpha radiation, 1 rad is about 200 millisieverts. Okay, so let's simplify this quite a bit because I am neither a physicist nor a radiologist. Let's remember that 500 millisieverts is the dosage where you start to see radiation poisoning. And 1 rad, at the highest conversion from rad to millisieverts that we have on the previous chart I showed, 1 rad is 200 millisieverts. So we can assume by these conversions, remember, I am admitting that they are rough, that 2.5 rads is about 500 millisieverts, aka where you start to see the effects of radiation poisoning. Now let's look at what the astronauts were exposed to. NASA also simplifies its data, taking the average from the 3 astronauts on 1 crew. And as you can see, the highest average radiation dose was on the Apollo 14 mission. The crew averaged 1.14 rads on their flight, through the Van Allen belts to the surface of the moon and back again. And I'm no math whiz, but I do know that 1.4 is less than 2.5. So let's put this into a different perspective so you actually understand how much radiation this is. We're going to use CT scans because they use X-rays, and according to our earlier charts, 1 rad of X-rays is about 10 millisieverts, which is actually where high doses of radiation start. 1 rad, aka 10 millisieverts, is the same dose of radiation as that of a CT scan of the abdomen and pelvis. So the Apollo astronauts going to the moon basically got a CT scan of their abdomens and pelvises, which is really not that much radiation. I've had like 15 of those CT scans in my life and I haven't mutated or grown a tail. At least, not yet. And what's always missing from the discussion of the Van Allen belts and the Apollo crews is how fast they actually flew through those belts. The spacecraft passed through the inner belt where radiation is strongest in a matter of minutes, and the spacecraft's skin was effective radiation shielding. It took hours to pass through the outer belt, but the radiation is so much lower there that it wasn't a problem. Really, the only strange effect of radiation on the crew was the strange light flashes they saw in their eyes when they were either blindfolded or just had their eyes closed. NASA suspected that it was actually cosmic rays hitting the backs of their eyes that were sort of creating this light flash, and actually had crews go blind, like cover their eyes and count the light flashes in a given time, so NASA could try to figure out where these rays were coming from and if that's what they actually were. And post-flight physicals found that there was no adverse effects to seeing these flashes on the astronauts' eyes or brains, which is a good thing. But then there's that engineer who says that we don't know how to fly through the Van Allen belts. I hear you yelling at me. Yes, I am aware of him and of the video. Again, people send it to me all the time. So this is the video, and the engineer in question, Kelly Smith, talks about radiation and developing a radiation shielding system for Orion, which, let's remember, even though it does use Apollo heritage and looks a lot like Apollo, is a totally different vehicle. In the video discussing shielding and the Van Allen belts, he says,
"Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. We must solve these challenges before we send people through this region of space."
He doesn't say that we've never done it, he says that we need to solve the problem for Orion. So, moral of the story, Apollo astronauts were hit with about the equivalent of a CT scan of the abdomen and pelvis on their missions to the moon. That is far, far from a lethal dose of radiation. So, we've flown through the Van Allen belts, and nobody died doing it. So we did go to the moon because you can fly through the Van Allen belts. So I hope this helps clarify the fact that we did in fact go to the moon and that radiation was not super devastating to the Apollo astronauts. But I know you guys are going to have more thoughts on this one, so please sound off in the comments below, and within those comments be sure to leave me questions and other ideas for things you would like to see covered in future episodes. Be sure to follow me on Twitter and on Instagram for daily vintage space-ish content, and for more videos every single week, subscribe right here so you never miss an episode.